Hi everyone, my name is Yasemin Vardar and I'm an assistant professor at the Cognitive Robotics Department of Delft University of Technology in the Netherlands.
Today, I will talk about a study that we did together with Katrin Kuchenbecker when I was a postdoctoral researcher at the Max Planck Institute for Intelligent Systems in her Haptic Intelligence department. Our study has been recently published in the Journal of Royal Society Interface, so after the talk, if you would like to learn more details, you can go ahead and read our paper. I don't think that I need to convince you about the impact of digitization of audio and visual information on our daily lives. Especially if we think about our last 2 years, our computers, smartphones, tablets became a substantial part of our lives. We shop through them, we communicate through them, we learn through them, we create through them, we even diagnose through them. So it's really hard to imagine a world where we cannot capture, process, and display audio-visual information. But what about tactile information? When we interact with the objects in the real world, we touch and feel their physical properties. But in the digital world, when we interact with the objects, for example, when we touch the images on our smartphones, we only feel cold and hard glass surface. Of course, the recent generation of these devices started to add some tactile effects, such as button clicks, some vibrations, some buzzes. But if we compare the richness of these effects to the ones that we feel in the real world, they are almost nothing. But there is hope. There are techniques to create rich tactile feedback on touch screens, and one of them is electrovibration. In this technique, the frictional forces between the user's fingertip and the touch screen is modulated by electrostatic forces. This technique is based on a physical theorem, which is called parallel plate capacitor theorem, which says that if we have two conductive plates separated with a dielectric, and if we send a voltage signal to one of these conductive plates, there will be an electrostatic force that will pull these plates together. So in this case, one of the conductive plates is the conductive layer of the touch screen, and the other one is the conductive tissues in our fingertip. And if we send the alternating voltage to the conductive layer of the touch screen, we induce the charges in our fingertip, which will pull our finger towards the touch screen in an alternating way. So when the users move their finger on the touch screen, this alternating electrostatic force will create an alternating friction force, which will be felt as a tactile effect. By changing the properties of this input voltage signal, we can create different tactile effects. So if we look at the electrostatic force formula, we can see that the magnitude of the generated force depends on the voltage drop at the contact, which depends on the electrical properties of the screen, our body, our skin, and the electrical properties of the whatever material is at the contact. And also the force depends on the area of this contact, thickness of this contact, and electrical permittivity of this contact. But what is this contact? If we look at the schematic, it looks like at the contact we have our stratum corneum, which is the outermost layer of our fingertip, and it has a perfect circular shape. But in reality, it's not like that. Here you see the image of my fingertip when I was keeping it stationary on the touch screen. The black regions show the parts that I was fully contacting to the screen. And as you can see here, these black regions are not circular or smooth. So at the contact, I have some skin, of course, and also I have air gap trapped between my fingerprints. And at the same time, you see this circular vapor shape that shows that I was sweating at the same time, which means that at the contact I have a little bit sweat. All of these things affect my uh, contact electrical properties. Also, when I move my finger, you will see that this contact is changing. It changes its shape, it's changing the contacted areas, and also I'm sure that it changes how much air gap that is trapped between my fingerprints and also the sweat. Ideally, a designer should be able to control what users feel independent of their touch interactions. And if we think about what kind of interactions that we do with the touch screen, they are much more complex than keeping fingers stationary or swiping it with one finger. We sometimes tap, we drag, we swipe, we use multiple fingers, we sometimes use multiple fingers from both hands. And all these conditions, all these touch interactions have different kind of contact conditions. And in this study, we aim to understand the perception and physics of such interactions on electrovibration displays. For this aim, we selected 4 touch interactions and 2 contact forces, which we thought they represent most of the core touch interactions on our touch screens. The ones that we selected were 2 fingers moving from the same hand, 1 finger stationary and 1 finger moving at the across hands, 1 finger moving and 1 finger stationary. And for the contact forces, we selected 1 Newton and zero point 0.5 Newton per finger as the average contact force. And for the touch interactions where fingers are moving, the average finger speed was 50 millimeter per second. We measured the detection thresholds of 15 participants while they were interacting with an electrovibration display actuated by 125 Hz electrovibration voltage. Each subject participated 8 different experiments as we had 4 touch interactions and 2 normal force conditions. The procedures were same for all experiments where participants interacted with the display twice in each trial. In one of these interactions, there was an electrovibration stimulus, in the other one there wasn't, and we asked subjects in which one they felt the stimulus, and depending on their answer, we adjusted the magnitude of the input voltage so that we could find the value that they can barely detect. And I need to say that because of the nonlinearity of the electrovibration first generation, if we send a pure 125 Hz voltage, the electrostatic force will be twice of this frequency, which is the 250 Hz for this case. So these are the results for the detection threshold voltages. As you can see here, the detection thresholds for the one finger moving condition is much smaller than compared to ones that we use 2 fingers or for the stationary condition. So we can say that both finger motion and contact by a second finger significantly affect what the user feels. What is surprising here is some people, like approximately 30% of the participants, could feel the electrovibration voltage when they had their fingers stationary. So this is a kind of surprising result because in the literature it is mostly stated that if there is no finger motion, there will be no electrovibration perception. However, these statements were generally just observations that nobody has conducted systematic psychophysical experiments before. And our results show that it is possible to generate perceivable electrostatic forces even there is no finger motion. So to understand why we had different threshold voltages for different conditions, we also measured the contact forces during the experiments, and we analyzed the forces for the trials that we calculated threshold voltages, and we found the magnitude of the electrostatic force by just looking at the power of 250 Hz signal because we knew that our electrovibration force will occur at that frequency. And here are the results. This is the force at the normal direction, and this is for the lateral direction. And what we found that the magnitude of the electrostatic force was the same for each moving finger. But we had different results for the stationary condition. Of course, since the finger was stationary, we almost had nothing in the lateral direction, but we had very large electrovibration, electrostatic force at the normal direction for the stationary conditions. And for example, for the 2 finger moving condition, the amount of force was almost twice because we had 2 fingers and we measured the forces for both fingers. And we also analyzed the electrostatic force magnitudes for all trials, and not only threshold voltages. And we fitted these electrostatic force magnitudes to a model. And you can see here that for different conditions, we had different constant K values. And what actually like these graphs show, so this is the results for the 0.5 Newton contact force, and these are the results for 1 Newton contact force. If we choose an arbitrary electrostatic force magnitude, so this is approximately the detection threshold we measured for each moving finger, we can see that for each different condition, we need different input voltages. And this input voltage value is very high for the stationary condition. And also it's much higher when we have one finger stationary and one finger moving condition. And uh, since we have two fingers, for the two fingers moving condition, we have to look at the twice of this value, and we can find out that this voltage is a little bit higher than the one finger moving condition. So as we see here, for different conditions, we need different input voltages to generate the same amount of electrostatic force magnitude, which shows that there is something happening at the contact. And if we recall our first hypothesis that if there are changes in the contact electrical impedance, there will be also changes in the electrovibration perception. So to really prove that, we also conducted another experiment with one participant where this person was interacting with the electrovibration display with all the touch interaction conditions. And here are the results. The first graph shows the electrical impedance measurements for different touch interactions measured at 0.5 Newton contact condition. And the second graph shows the same for 1 Newton contact condition. As you can see here, for different touch interactions, we have different electrical impedance results. For example, for the one finger moving condition, we have the highest impedance, and two fingers moving condition, we have almost half of this uh, impedance. And for the other conditions like one finger stationary or one finger stationary and moving condition, we have much lower electrical impedance. But if we compare the results of the two contact force conditions, this difference is not too much striking. And then we fit these electrical impedance measurements to a simple electrical circuit model so that we can understand how different touch interaction conditions affect the electrical properties at the contact. I will not go into details of this model or the results of it, but in short, I can say that the changes in electrovibration perception were caused by the changes at the contact electrical impedance. And both using multiple fingers and finger motion significantly affect the contact electrical impedance and consequently electrovibration perception. So that was the end of the story. But before I finish my talk, I would like to acknowledge some people. First of all, I would like to thank to my co-author, Catherine Kuchenbecker, for her significant contributions in this study. And then I would like to thank Bernard Devot for his help in the experimental setup design. Also, I would like to thank Gökhan Serhat and Caroline Keo for their useful discussions and suggestions during the study. Also, I would like to thank anonymous reviewers for their help in this process. Their suggestions improved the paper significantly. And also, I would like to thank everyone in the Haptic Intelligence Department for their help and support during this project. So thank you very much for listening. And if you have any questions, I can take them now.